Welcome back to Chem 4300. In this video, we're going to finish up Chapter 16 on the quantum particle in 3 dimensions. And the last short thing we have to do is to work out what are the eigenstates for the angular momentum operators. So let's take a look at this. So we'll go back to the expression that we had at the beginning of the last video, which was the angular momentum was r cross p, which in the position basis we write as minus I h bar r cross the gradient operator. Now, if we're going to work out what the eigenstates or the eigenfunctions of the L squared and LZ operator are, we need to go into a coordinate system that's going to be more friendly for what we want to do. So what we're going to do is we're going to switch from a Cartesian coordinate system to a spherical coordinate system. And we've done this many times now in this course. So remember these unit operators in the spherical basis compared to the unit operators in the Cartesian basis. So we write these operators in terms of the Cartesian unit operators and vice versa here. And that allows us to rewrite the gradient operator in terms of spherical coordinates as shown here. So again, this is what we need to express the angular momentum operator in terms of spherical coordinates, and we have that now here with this conversion. So armed with this, then, let's look at what the components of the angular momentum operator, or the LZ component, and the L squared component look like. So here's what we have for Lx, Ly, and Lz, and I'll leave this for you to derive here. The simplest one of these is just Lz, which is just I minus IH bar, and then the partial with respect to phi, whereas Lx and Ly depend on both theta and phi. The L squared operator, which is just the sum of the squares for the components, is going to be minus IH bar times this expression here. So now we've got, with our conversion to the spherical coordinates, the form of the operators which we first derived in Cartesian operators. We now have it in terms of spherical coordinates. So let's keep going. If we want to get the eigenfunction for both L squared and Lz, let's start with the simplest one, which is the Lz, right? Lz operator is just this. If we write down Lz operating on the wave function, we have IH bar over I d phi, d psi, d phi, right? And of course, we know the eigenvalue for this. We just proved this in the last video. So we know that when Lz operates on psi, we get back m times h bar times psi, where m is a value that goes from minus L to L, with L taking on values of increasing with values of integer. So minus L to minus L plus 1, minus L plus 2, all the way to plus L. Now, what we're going to do is we're going to solve this differential equation by assuming we can do a separation of variables for our guess, which if it works, then it will be a good guess. And we will plug that into this expression here, and you see that that gives us this expression here. And what we find is that actually when you take the derivative, the theta part is on both sides. It doesn't really do anything. We can simplify this, and it simplifies down to this expression here, where we remove the h bar, remove the theta dependence, and we have only a phi dependence, which we can rearrange into this form. And now we have a very, very simple differential equation to solve, which has this solution here. So that's the solution for the phi part of this wave function. And what we can see is that we expect that all of our wave functions should not only be continuous, but also be single valued, right? So we know that if this is a function of phi, that if phi goes around 2 pi, that the function has to come back to the same value, right? As we go around in a circle, we should come back to the same value. We shouldn't have some gap between the values of the wave function when we go 2 pi. So we expect these guys to be equal. That gives us, if I put in this on this side and this on this side, I get this equation here. Simplify that a bit, I get e to the I m 2 pi has to be equal to 1, and that requires, for this to be true, m has to be equal to values of 0, plus or minus 1, plus or minus 2, and so on. So that's consistent with what we had saw earlier. Now, next we're going to consider the L squared term, and we want to see if we can work out the rest of the derivation of this for the full theta and phi dependence. And we know that L squared operating on the wave function is going to give us this eigenvalue, which we proved in the last video. So if I take in that full expression for L squared, which we just derived a couple slides ago, and I put all of this in here, into there, equal to the eigenvalue times the wave function again, then I'm going to substitute in my guess once again, plug it into that expression, and divide, after dividing both sides, I can get it into this form where I have everything that depends on theta on this side and everything that depends on phi on that side. And of course, this part we already know. We can set this equal to a separation constant as m squared. And at this point, you're looking at this and thinking, this looks familiar. And that's right, it does look familiar. We did this already. We did this in the classical wave chapter. It's the exact same partial differential equation, and we saw that the solutions to this were the spherical harmonics. So we don't need to go any further. We know now that the eigenstates of the angular momentum operators L squared and Lz are going to be simply the spherical harmonic wave functions. So we've seen this before, we derived them, so we now have the answer. So we know the eigenvalues and we know the eigenstates for the angular momentum operators. So in this chapter we learned a lot of really important, it was kind of tedious with some of the derivations, but we learned some really important properties of angular momentum, which are going to be very important when we look at systems like an electron orbiting an atom and having angular momentum, and all those properties that we're deriving here, we're going to leverage as we look at more complicated quantum mechanical systems describing atoms and molecules.